Moon, a clue to understanding geological processes.
Thanks. So we look at the steepest slopes on the moon. Why do we do this? By the way, this is one of examples of not the very steep, but a really steep slope of the moon, Apollo 15 landing. So, steeper slopes are interesting. They give us some ideas about processes. Not all geological processes can create very steep slopes. Then very steep slopes tend to degrade with time, so we can have some clues about time. I will show you how this works in first steps, and we can continue after that. How we do this? We use LoLa data, laser altimeter data. They give us advantage of uniform coverage over the whole planet. So image data are not good for this because they depend on sun elevation. We are interested. It is interesting for us to use the shortest possible baselines. This gives us more and more interesting steep slopes. So we use the fact that each laser shot was split into 5 beams, and each LoLa shot gave us 5 measurements of elevation. From them, we can take any 3 and calculate topographic gradient, and its absolute value is slope at 25-meter baseline. And from each shot, we calculate 1, 2, 3, 4 of these slopes. So totally and we use circular orbit. So totally it is more than 2 billion slope measurements over the whole planet. This is slope frequency distribution with linear scale and logarithmic scale. So most frequent slopes are just a couple of degrees. Typical slopes, median like 7.5 degrees. Somewhere here you see long tail in slope frequency distribution, and we are interested in these 0.2% of the steepest slopes, very rare very steep slopes. In this logarithmic plot, you see that this long shoulder, long tail of the distribution has noticeable break here. It is certainly related to angle of repose. So we are interested with slopes steeper or comparable to the angle of repose. This is global map of global image mosaic of the moon, and slopes steeper than 35 degrees are marked with yellow, and you see association with different geological features. And it is interesting to look how slopes change when we go from somewhere here in this plot to more and more frequent and gentle slopes. And this is this series. So these are very, very steep, steeper than 45 degrees, real cliffs. And if you look at concentration of black dots here, they all are associated with young craters. You can recognize that this is Tycho, this is Copernicus. And they have very, very steep cliffs, and they are only the youngest large craters on the moon. If we consider more gentle slopes, 40 degrees, here we start seeing other features. Somewhat older Eratosthenian age craters, as well as Orientale Basin. For even gentler slopes, it's much more slopes. We clearly see all Eratosthenian age craters, and we start seeing some late Imbrium age craters. Iridium, for example, this one. And finally, for even gentler slopes, we clearly see Orientale. We see some secondaries of Tycho. We clearly see a number of late Imbrium age craters. So this how this works. It is interesting that we see almost no slopes steeper than 32 degrees and absolutely no slopes steeper than 35 degrees for any crater older than late to early Imbrian boundary. The only is this is Imbrium outer circle Montes Apenninus, and here we see steep slopes. So Imbrium impact is early Imbrian. So this is the only slope of early Imbrian age that is really steep. Only one exception. So this is summary of observations I just tell you, and it is not seen at that scale. If you look at a larger scale on computer screen, you also see that there are some steep slopes associated with sinuous rills and some tectonic features like those fractures in craters you just saw in images. They are never very steep, but they still in our list of the steepest slopes on the moon. So our interpretation. First, we see that all pre-orientale impact. Okay, we see that old craters don't have steep slopes. Our interpretation that each basin-forming impact erases all pre-existing very steep slopes. This occurs due to global seismic shaking. That's why we don't see steep slopes that predate the latest basin-forming impact, which is Orientale basin impact. Then, after Orientale impact, we see gradual degradation of the steepest slopes. 45-degree slopes are only for the youngest craters. This is our interpretation to what we see. This gives us useful tools to look at craters. For example, it is some independent measure of stratigraphic age of craters. If we see very steep slopes on a crater, we can suggest that it has young age, regardless of cratering count, superposed crater counts, and some other things. So it is another independent way to see at stratigraphy. Tectonic features are consistent with this. Most of them are late Imbrian in age, so consistent that they don't have 45-degree steep slopes, they have 35-degree steep slopes. Another interesting thing is global distribution of the steepest slopes on the moon. This is what we see if we bin proportion of slopes steeper than 35 degrees in narrow latitudinal bins. We see very huge noise, and actually each peak corresponds to some young crater. This is Tycho, for example. So to see if there is some global pattern, we need to smooth this curve very significantly, and we did this through spherical harmonic analysis. And when we smooth everything down to spherical harmonics of degree 5, we have this curve. You see some excess of steep slopes in equatorial region. So this is proportion of steep slopes among all slopes normalized to global average. Why this can happen? Our explanation that probably it can be related to rate of formation of young craters. There are some theoretical predictions that cratering rate at lunar equator is higher than at the poles. And green curve here is one prediction from one of the papers where they consider this. Well, this is considered theoretically. So you see that amplitude of the signal VC and predicted difference in rates of young crater formation is more or less the same. So it looks reasonable. But however, things are not that simple. If we consider global distribution on the sphere, on the whole moon, it is not that simple. So this is our map of proportion of steepest slopes smoothed down to spherical harmonics of degree 3. We do see concentration to equator, but this is what was predicted from theoretical considerations of impact frequency. We do see concentration in leading hemisphere, so this is simple cylindrical projection for the whole moon, so this is a leading hemisphere. But it is not exactly, it shifted to the west, to the far side. And surprisingly, we see much better correlation with topography. So actually the maximum in occurrence of the steepest slopes correspond to the highest elevations on the moon and not to the leading point of the moon. Another feature is a relative deficiency of very steep slopes in southern far side, more or less coinciding with South Pole Aitken Basin. And these are the lowest part of the planet, and this is surprising. Here we see topographic roughness. Topographic roughness is different from steepest slopes. Topographic roughness deals with gentle slopes and elevations of meter scale, not tens of meter scale. So it is different thing. It is related to regolith gardening, not to large scale geology. And we see very good correlation with topography and proportion of steep slopes that we observe. And these correlations are puzzling. We don't have good explanation for this. Well, and this is more or less our conclusions, so that steep slopes are useful, and we see this removal of all steep slopes by oriental impact and gradual decrease of slopes with time. And we see these puzzles, and we need to solve them. Thank you.
We have time for questions.
Yes. Misha, that's very interesting work. Carly Peters, Brown University. One of the things, the processes that you didn't list in the things you identified or examined was and I'm not sure how to measure it, essentially it's textural. Megaregolith versus coherent rock, which would clearly have a distinct effect on the degree to which a slope can be maintained. You might, for example, see if there's any link between crater size or depth of excavation.
Well, I had only 15 minutes. So if you look at Taika, you see that very steep slopes are through the whole crater. So even small blocks, if they are tall enough at the crater floor, have steep slopes. When you go to all the craters like these, you see that floor is free of steep slopes. So when you produce some regolith layer, you disintegrate these smaller blocks, and very steep slopes are only on large crater walls. Well, this is something in.
No, that's a good argument, but I'm looking at your Oriental, and isn't that the inner ring?
Inner ring is here. Most expressed is outer ring, yes.
Oh,
but
okay.
We do see some steep slopes in inner ring too.
Okay. Okay, very interesting.
Bill Bodke, Southwest Research Institute. This is really interesting, and I think some of your results seem to be very similar to work that I've been doing some work with Becky Gent and her student on diviner data, looking for sort of the blockiness of materials. And one thing that I think we've seen in the data to some degree is a lack of lots of blocks associated with fresh craters in SPA. And it seems to me that's a case where you're not getting much surface roughness as well. So could it just be that the intrinsic weakness of the material, or the material is more beat up or chewed up, is preventing you from getting very steep slopes? Is that the correlation that we're talking about here? Maybe you can show the slide with topography and roughness and then slope. Yeah, so I'm wondering if roughness means the ability to make sharp, craggy, big rocks. If where you have dark there, it's hard to do that. That also seems to line up where it's very hard for you to get steep slopes. So I wonder if there's a correlation there. And the same thing with topography. You just can't make steep things, right? So it's all works together.
If I remember correctly, in radar data, you see higher return here. Is that correct?
Oh, I don't. Well, I know they can't see SPA from ground-based radar. Do we have other radar? Maybe Clementine?
Well,
I don't know the answer to that.
Yeah, so
Oh, there you go. Okay.
tomorrow at 10:50 in the other room, I'll be talking about, but yeah, mini-RF global data shows SPA to be distinct, but has a thick regolith with small scatterers, 1 to 2 meters thick. So it is distinct, but there's something weird going on. But yeah, we've got global radar data from mini-RF. Come on, man.
Oh, mini-RF, yeah. Okay, I'm an old scientist, right? I forget these new things. So these newfangled machines.
But the radar, I think.
yeah. Anyway, I think that there might be correlation. We don't understand what is correlation here, what is primary, what is secondary. Yeah. And roughness and steep slopes are different processes, because roughness deals with meter size vertical scale, steep slopes deal with tens of meter size vertical scales. Sure. And radar deals with up at decimeters like this. So this may be occasional, this may be some reason for them to correlate.
It's really interesting. Yeah, we should talk, not at the microphone.
Any final questions? Okay. Thank you all very much on behalf of my co-chair,